Okay, welcome everyone to this afternoon session. We're going to start with two talks. One will be in presence and the second one will be online. And then we have a workshop on machine learning, which will be also partly online and partly here in presence. So for now, let's all welcome Saurabh Rathore from IIT Delhi for the first talk of the afternoon session.
Yeah, so good afternoon, everyone. I hope you are not sleepy after the lunch, but I would like to take you away from the human intelligence towards the machine intelligence. It's called machine learning or artificial intelligence. So you can see that the title of the talk is the detection of Mesoscale arrays using explainable deep learning model in the Bay of Bengal. Okay, so this work has been done by one of my internship students, Joyjit Mandal. So I'm going to present this work on behalf of him. So we know that what are the mesoscale arrays by now, because there were many talks on the mesoscale arrays. So if you can see that this is the east coast of the US and this is the Gulf Stream. This is a warm the warm current, and these ring structures that are shedding off from the Gulf Stream, they are known as the eddies, the mesoscale eddies. And these eddies are present both in ocean and atmosphere, and the oceanic eddies are often called as a weather of the ocean. So there are two type of eddies, anticyclonic, cyclonic, based on their sense of rotation. So whatever they, let's talk about the northern hemisphere. So whatever they have a sense of rotation in the northern hemisphere, it is opposite, they are going to have the opposite sense of rotation in the southern hemisphere. Okay. So the spatial scale of those eddies are like 10 to 100 kilometers, lifespan of 2 to 10 months. Okay, and they play a very crucial role in transporting the heat and nutrients and the salt of the ocean from one place to other place. Okay, and they are considered as like a low understanding of these mesoscale eddies are considered as a missing link between the mesoscale dynamics of the ocean to a big picture of climate. Okay, so these are the active area of research at the moment. To understand the big picture, we need to understand that how eddies are behaving in the ocean, how they are transporting the heat, carbon, and nutrient, affecting the ecology and the biogeochemistry of the ocean. So this is a schematic that shows that how the mesoscale eddies having their sense of rotation. So this is the cyclonic eddy, which is anti-clockwise, and it is in the northern hemisphere. And similarly, we have the anticyclonic eddy, which is in the clockwise direction in the northern hemisphere. And in the southern hemisphere, they are in the opposite sense of rotation, which means cyclonic eddy will rotate clockwise and the anticyclonic eddies will rotate anti-clockwise in the southern hemisphere. So this picture shows the Bay of Bengal region, which is bounded by this location here, and this color shows the sea level anomaly. Okay, and these vectors shows the geostrophic vectors. So wherever we have the sea level anomaly as blue, which is a negative anomaly, and red color is a positive anomaly. So this negative anomaly are often for the northern hemisphere resembles the cyclonic eddy, and this red color, which is the positive anomaly of the sea level, often resembles as a anticyclonic eddies. Okay, and these geostrophic vectors which are overlaid on this color will give us the sense of rotation. So if we talk about this thing, so this is negative sea level anomaly, and which is anti-clockwise on the geostrophic vector, which means it's a cyclonic eddy. And if you talk about this red color, so this red color is the positive sea level anomaly, and we call it as a anticyclonic eddy. Okay, so the eddies having a very distinct signatures on the properties of the ocean. So if you talk about the anticyclonic eddies, so wherever we are having anticyclonic eddy, we can find a drop in sea level. There is a drop in sea surface temperature. Sea surface temperature drop means there is a huge region of upwelling. So the cold water will come to the surface and the sea surface temperature will get dropped. Okay, and whenever we are having this upwelling, okay, so this upwelling will bring a lot of nutrient from the ocean subsurface, and it will come toward the surface, and it will increase the biological productivity of the ocean. So that is why we are having the high amount of fish catches. Okay, So whenever there is the abundance of the nutrients available on the ocean surface, so the fish attracts towards it, and there's a high amount of biological activity, and we can catch the fish. But opposite to it, if you talk of the anticyclonic eddy, so these are high in the sea level because there's a convergence area. So if there is a convergence area, so there is a rise in the sea level. So whenever there is a rise in sea level, we are getting rise in sea surface temperature, and because of that, we are getting the downwelling. So whatever be the surface property we are having, it got subducted into the ocean. Okay, and that is why all the nutrients which are present on the surface, which can serve as a food to the fish, now they go down into the ocean, and there's a drop in the biological productivity. Okay, so the cyclonic eddies are responsible for the high biological productivity, and the anticyclonic eddies are responsible for the low biological productivity in the ocean. Then let's talk about that how to detect the mesoscale eddies. Okay, so there are certain packages or certain algorithms available to detect the mesoscale eddies in the ocean. So I'm going to describe like a few of the packages here. So these packages are based on either on the physical feature-based method or on the geometrical feature-based method. Okay. So the physical feature-based method, we are talking about the Okubo-Wiss parameter. Okay. Okubo-Wiss parameter is developed by Okubo and Wiss in 1970-1991, and which is served as a sort of a detection algorithm for the mesoscale eddies in the ocean. Okay. So we can talk about the Okubo-Wiss parameter, which is W. Then we are having these three terms, and these three terms are described as normal strain, shear strain, and relative vorticity. The normal strain is the stretching and compression of the fluid parcel. Okay, so the fluid parcel will get stretched or fluid particle will get compressed. Okay, so this is known as the stretching and compression of the fluid parcel about a specific axis. Then we are having shear strain. So shear strain means there is a deformation in the size. Okay, so typically if we think that the eddies are circular, right? The vortices are circular, but they are not the case in the real world scenario. The oceanic eddies, they are of any sort of size. Okay, so it depends on this deformation thing, which is our shear strain. And then we are having the relative vorticity. So the relative vorticity gives them the circular motion, which is a rotation of a fluid parcel about a relative axis related to its neighbor. So this is one of the method that is a very traditional method that is still in use to detect the mesoscale eddies in the ocean. Then we have geometrical feature-based method. So these methods like used in many literature. One is from Mason et al. And one is from Fagmos. Okay, so Fagmos is the latest one. So in this Fagmos method, so they detect the eddy based on some geometrical constraint, such as the closed contours. The sea level anomaly should have a closed contours, and then only we can call it as a eddy. Okay. Then we have circularity. So it should be circular in size, which is not the case in the real world scenario. This is the case that they are taking to call it as an eddy. Then based on their size, shape, and area. So these methods, they are very much susceptible for the human understanding that, okay, I can call it as an eddy based on certain features. Okay, so we are constraining, or we are restraining ourselves, okay, to explore the other part which we cannot understand as an eddy. Okay, so that is why these methods, they are based on a certain features, and they are constrained by our understanding. Okay, so to overcome this deficiency, we have to go with the detection of the mesoscale eddies using machine learning or the artificial intelligence. So our task is to detect the eddy in the Bay of Bengal here. Okay, so this is the Bay of Bengal, and we are going to use a deep learning model. So previous studies have shown there are various deep learning models for the detection of the mesoscale eddies. Okay, and we are going to use one of them. And this sort of work has been done in the South China Sea and the South Atlantic, but not so in the Bay of Bengal. Okay, and here we are trying to develop an deep learning model for the detection of mesoscale eddies in the Bay of Bengal. So they are the sort of literatures that they have used a deep learning model for the detection of the eddy. So which is often known as like a convolutional neural network, which is based on like some encoder and decoder layer, and they call it the EddyNet. Okay, and the same sort of model with a different approaches has been used so far. Okay, in 2020, 2022. So in 2020 they use a multi-model data approach, like multi-data approach, to detect the eddy. but they all are based on some convolutional neural network, that is the image processing deep learning algorithm. Okay, so we have to give an image, so the model has to detect the features out of it, and then it will generate a prediction. So this is a methodology that we first have to provide the data, then we have to create a segmentation mask. Okay, I will explain what is a segmentation mask. Then we have to train the model, then we have to apply a sort of filtering, and there is a reason that why we need to apply a filtering, and then we have to compute the performance of our model, and then we will have a look on the explainability of the deep learning model, that is known as the explainable AI. So this is the data. So the data source is from Siemens, that is the Copernicus Marine and Environmental Services. And from this we can get the sea level anomaly data. This is the DOI, if you can download the data for yourself. So we have downloaded the data for the Bay of Bengal from 1993 to 2023. Then let's come to the segmentation mask generation. So how we can generate the segmentation mask? So first of all, we need to detect the eddies from the SLA data, from the sea level anomaly data, we have to detect the eddies. So this is the eddy detection that we did using these two available packages that are the traditional packages to detect the eddies in the ocean. One is the Pi eddy tracker by Meson, and one is the Open Eddy from Phagmos. So I personally believe that Phagmos is better than Pi eddy tracker, but it's very subjective. Okay, you can choose any of the models you like. So after detecting the eddy, we need to generate a mask. Okay, where we have to differentiate the eddies from the background. Okay, so here we can see that there are two sort of colors. One is a sea green color, one is a yellow color. Okay, this yellow color is a cyclonic eddy, and this sea green color is a anticyclonic eddy, and the background is purple or violet. Okay, so we have to generate a mask in such a way that wherever we are having a cyclonic eddy, let's say it's 1. Wherever we are having anticyclonic eddy, let's call it 0. Okay, and other than those two, we are having the background. Okay, so there are 3 features. One is cyclonic, anticyclonic, and then there's a background. So there are 3 features present in this picture. Okay, so this is the Pi eddy tracker segmentation mask, and this is a Phagmos, that is the Open Eddy segmentation mask. So you can see that there's a wide difference between these two traditional eddy detection algorithm. Okay, so here you can see that the Pi eddy tracker often detect all sort of eddies. Okay, that is big, small, okay, all sort of eddies. But Open Eddy is only focused on the big size eddies. Okay, relative to the Pi eddy tracker. So suppose if this is the case, okay, so this is a very small eddy. Okay, so this type of eddy, or like this type of eddy, is not present in the Open Eddy software. So there's a difference in the ground truth data as well. Okay, suppose if you want to give this data, so it will generate a different output. The model will get a different training data set. Okay, so this Pi eddy tracker, they often detect a large number of eddies as compared to the Open Eddy software, like the Phagmos. Okay, so here we are having our training data set from 1993 to 2016. So training data set means we have to give the segmentation masks to the deep learning model for the training. So we have to detect the eddies and create a segmentation mask from 1993 to 2016. Then our validation period is like 2017 to 2018. And then we have our prediction, that is the testing data set for 2019 to 2023. So as I explained that the previous literatures have used a sort of a convolutional neural network. Okay, and here we are also going to use one model architecture which is called as UNet. So UNet means because it shapes like a alphabet U, that is why we call it as a UNet. Okay, so this is a sort of deep learning model that is often used by many researchers to detect the mesoscale eddies. Okay, so this UNet is a convolutional neural network, and we can see that the shape and size of this matrix is changed in every layer. So as you go down in the bottom level, so it become more wider. Okay, so this is the width, and then this is the length. So it becomes squeezed and become wider. Okay, so this is a layer of the, or you can say the matrix that goes to this convolutional neural network. So this part is the decoder part. Sorry, this part is the encoder part. So it takes the input, it takes the sea level anomaly pictures or sea level anomaly maps. Okay, then it do some kind of statistical processing, and then this is the encoder part, and it gives us the output. So as we go up in the encoder part, this squeeziness will again come to a normal size. So this is a typical UNet structure. Because of its U shape, it is called as UNet. Then the advanced version of this unit is the attention unit. So the attention unit, the only difference between this and that is we are going to have a attention gate here. So on the encoder side, on the decoder side, we are having an attention gate. So this attention gate will is consist of like a ReLU function. Okay, ReLU function. So ReLU is on like a rectified linear. I forgot the name, rectified linear something. Okay, so it is like an activation function, which means if the output is 1, it will give you 1. Okay, and when the output is negative, it will give you 0. So it is sort of a maximizing function. It will maximize the thing. Okay, when the output is 1, it will give you 1, and then when the output is positive, it will give you 1, and when the output is negative, it will give you 0. So the only difference between UNet and attention unit is this attention gate. Okay, so the attention gate is always situated on the decoder side of the convolutional neural network. So how deep learning model works? So in this thing, we have, these are our input images from the satellite data for the sea level anomaly. So we have to give this input images of the sea level anomaly to train our model. Okay, and we have also gave this segmentation mask. So the segmentation mask has been generated from the traditional algorithm, that is the PyD tracker or the OpenAD software. Okay, so we have to generate this segmentation mask as well, and we have to give these two things to our deep learning model. So our deep learning model will look into this picture and get this feature, and then compare it and then train itself. Okay, so this model will learn that okay, my eddy will look like this. Okay, so whenever I will get such kind of thing, okay, I have to call it as an eddy. So the deep learning model train in that way. And then after training the model, we have to give the sea level anomaly data, that is the testing data that is not seen by the model. Okay, so we have to give this data to our deep learning model, and the deep learning model makes some prediction, and it will detect the eddies based on the training of the model. So now let's come to filtering. Why filtering is important? As I mentioned that our traditional algorithm, that is the PyD tracker, often detect a large number of eddies of, okay, even though it is small or big, it detects all sorts of eddies. So suppose if we are training our model on such an algorithm which detect all sort of eddies, okay, of a very small size to a very big size. So our training is itself in a wrong way. Okay, so if we look that after generating this or after getting the segmentation mask, we can see that there are some sort of pixels here, right? So these are the pixels that the deep learning model or the PyD tracker consider it as an eddy. But in our physical understanding, these are not the eddies. Okay, they are not the eddies, because the eddies are not so small. Okay, there might be some sub-mesoscale features or something, or some noise of the data, but they are not the eddies. Okay, so that's why we have to apply the filtering, and in filtering we have to say that if we are getting a feature which encompasses less than 4 pixel, we have to neglect that feature. Okay, because we are considering this as a noise. Now why we have to do it? Because suppose if you want to compute the eddy statistics like the mean radius, mean amplitude, and other sort of statistics, so if we are counting these also as an eddy, it will give the false indication of the statistics. That is why we have to be very careful that we have to remove such noise before doing the eddy statistics. Okay, and that is why we have to do the filtering, and after filtering we can see that these sort of pixels are not present here. Okay, so it's very subjective. So for us, we did, if the deep learning model or the traditional algorithm detecting an eddy less than 4 pixel, we are removing it. Okay, we don't want that. Then let's come to the explainability of the deep learning. So why explainability is needed? Because it is said that the machine learning or the AI models, they work as a black box. Okay, so people are trying a lot and making a lot of effort to understand that if a deep learning model is going to make a prediction, why it is going to make such prediction. Okay, so they want to explain the black box part of the model, that why the model is going to give such kind of prediction. Okay, so for this we have to go for the explainability of the model. Okay, and this is known as the explainable AI. So for the explainable AI, we use a ready-made package in the Python. It's called CGradCAM, and it's a gradient-based method for interpreting the prediction done by the deep learning model. Okay, and it is also based on this ReLU function, which is a rectified linear unit function. Okay, and because of this, I will show that how we can explain the detected eddy from the deep learning model. And then the metrics called model performance. So for the model performance, like how good our deep learning model is. Okay, so for this we have to use a metric called intersection over union, that is IOU score. Okay, so let's say this is the segmentation mask that is developed by the PyID tracker or the FEGMOS algorithm. Okay, and this is the segmentation or the detected eddies from the deep learning model. Okay, now we can see that a few of the eddies which are present in the detected, they are also present in the ground truth data. Okay, which means they are intersection, they are the common eddies. Okay, and the total area of the eddies, like if we do the union of these two data set, we'll get the total area of the total area of the mask that we have created. So our IOU score is the intersection of the eddies divided by the total area. Okay, so if this intersection is less, we can say our model performance is not so good, and when this intersection is more, we can say our model performance is good. So we are always trying to go closer to the reality or closer to the ground truth data. Okay, that is why we call it as a high IOU score or low IOU score. So generally it has been seen that the attention unit is performing better than the unit, but in our case, if you look for the numbers for the for every sort of things like the background, mean, and anticyclonic and cyclonic in both traditional algorithms like PyID tracker or the OpenED, these numbers are same, which means we need not to go for a very complicated architecture of the deep learning model. A simple architecture is also sufficient to detect that eddies. Okay, but we are still going to use the attention unit with filtering process. So so this is the thing that these are the input that we have to give to our deep learning model for the training, and then these are the eddy detected by our traditional algorithm, and these are the prediction made by our traditional algorithm. Okay, and they are same for the OpenED software. So this from the PyID tracker, this from the OpenED software. Okay, so you can clearly see that there are some eddies which are detected by the PyID tracker, that is a traditional detection algorithm. So let's talk about like this as an detected eddy from the traditional algorithm, but our deep learning is not able to detect that eddy. Now if we see here, if you see for this yellow thing, and the yellow thing is like cyclonic eddy, so it should be an eddy here. So there should be an eddy here in a cyclonic way, but we are not finding any eddy here. So the PyID tracker doing a mistake. Okay, so it is because it is based on like human knowledge and some constraint with geometrics and all. So it is detecting an eddy which is actually not an eddy, and this has been called out by the deep learning model. So deep learning model is not showing this an eddy. Okay, which means our traditional algorithms, they might detecting an eddy which is not an eddy. Okay, and the deep learning model is well enough to capture that feature, that this is not the eddy which is not present in the deep learning. So in such way, the deep learning is a better approach to detect the eddy as compared to the traditional algorithms. Then there are some eddy statistics we can see for the PyID tracker and for the OpenED. So this is the area histogram. So area histogram is like if we detect an eddy, we have to count the number of pixels and multiply with 100 into 100 kilometers to get the area of the eddy. Okay. So if you go for the small area, we can see a high number of eddies. Okay. So large number of eddies consist of the smaller areas. But as we go for the bigger size area, bigger size eddies, so they are very less in number. Okay, so this histogram tells us two things. One is that our deep learning model is doing good because it is following the curve of the histogram, which is detected by the traditional software. And if it is like the less number of eddies consist of the less area, which means the high eddies are concentrated for the less area, and as we increase the area, so the bigger size eddies are very less in area, or very less in number. And similarly, we are having for the amplitude. So amplitude is the maximum and minimum sea surface height that we can get at the center of the eddy related to the environment, like the surrounding of the eddy. Okay, so this PyD tracker and the open eddy, they are shown in blue, and this is the detection from the deep learning model. So the deep learning model is capturing the behavior of the of this sort of statistics in the eddy, or the amplitude of the eddy. So the scientific thing is like higher the amplitude, lower the amplitude, higher the number of the eddies, and higher the amplitude, lower the number of the eddies. Then if we talk about the correlation between the detected eddies and the eddies, the eddy detected from the traditional algorithm and the deep learning, so we can see that the traditional detection of the eddies and the deep learning showing a very good correlation.
Excuse me, Saurabh. Your time is up. Could you maybe speak up a little bit?
And this is the explainability. Explainability shows that this part of eddy is well explained by this sort of thing, and this pixel is important for the explainability of this eddy. So this is the importance factor. So higher the importance factor means the pixels are very, very important for the prediction of that eddy. So this is the explainable AI. So these are conclusion that we still need a better architecture for the prediction of the eddy, and we need to improve our ground truth data, that the detection eddy algorithm to detect the eddies in a good way. And thank you.
Thank you. Anybody has a question? Maybe we have time for one till we move on.
So I don't quite understand. Okay, I guess one criticism of your IOU score is that if your ground truth is flawed, or you could argue it for it to be flawed, then the IOU score doesn't mean anything, right? So it just tells you that if your ground truth itself is flawed and you have a high IOU score, then it's just, in some ways, it's just telling you your model is able to reproduce the ground truth. But then the ground truth itself is, if it's flawed, then it just means the predictions are meaningless.
No, actually, the ground truth is not completely flawed. It is like at few places it can detect an eddy which are not physically an eddy. Okay, but it is not completely wrong. Otherwise, there is no meaning of the previous studies, right?
Well, then I guess does this not depend on how you define your estimate? So how you define your eddies depend on what scientific question you're trying to ask, right? So let's suppose in your case you're trying to, in your motivation, you were saying how your eddies are possibly related to biological activity. So most of that would be related to transport. But then is it necessarily true that from diagnosing an eddy from an Eulerian point of view necessarily gives you something which is related to the material transport?
So in this thing, we are just trying to detect an eddy. We are not trying to understand that how it gonna affect the system, like as a whole, like if it's going to transport any property or not. So our first task is just to detect an eddy. Are we able to detect an eddy?
Okay, maybe the discussion can continue in the future. Thank you again.